I think we are going to go ahead and start right away. We have a room full of people in here in our Seattle office. Thanks for the people joining us as well online. Like I said, for you guys, we are going to talk a little bit about the new 2023 features. So the software set to launch this month. We have kind of the final features that are ready to go. So I'll demonstrate that. And hopefully in a couple of weeks, you can all install it as well and start updating your licenses if you have an active software maintenance agreement with us or if you recently bought a system. It's actually, I think, quite exciting, the amount of features that we got this year. And kind of for the first time in 3 or 4 years, we pretty much have all those features applicable for pretty much everyone. You will all benefit from at least half of these new features. We had a lot of developments that were specifically big projects for niche certain types of customers. But this year, we have a lot to talk about. So I'll go quickly through these, and we'll do a couple of example and demonstrations of those features inside of the 2023 software in a minute here. But first, well, actually, before I even start about the list of features, I should say the software is changing name. It's the same platform. It's still under the ZEISS Quality Suites. Some of you have known it for a couple of years under the name ARAMIS itself. ARAMIS now refers solely to the sensor itself. So what's the cameras that we're using connecting into the platform, into the ZEISS Quality Suites. And our software also kind of changed name and is fully called ZEISS INSPECT for 3D testing, or ZEISS INSPECT Correlate, but you won't see any reference of the name GOM anymore. So those of you that are used to hearing GOM, it's being replaced officially by ZEISS. Again, as part of adding more and more different hardware platforms into the suite, we have now new line scanners, handheld scanners, 3D Inspect, CMM platforms as well that are all being thrown into the mix. We are a little bit behind schedule on the release, like I mentioned to everybody here. Because of all of these new product lines that are added, they found some bugs in certain lines, and so we are delaying so you have a reliable and steady installation once it comes out to your machines. So list of features here that I'll kind of go through really quickly at the beginning, and then we'll take a little bit more time towards the end. So first, we have GPU Facet Matching, which will speed up your processing times. We have new colors of surface components to increase visual and just ease of use of the software in general. We've worked a lot actually on trying to optimize a little bit and tweaking some of the workflows. So updated measurement sequences to just make it a little bit easier, especially if you have more entry-level solutions and systems. Updated orientation workflows, how to do calibrations for 2D and 3D, just simplifying that. We have an amazing feature for auto masking that way you'll also speed up your data savings and just the amount of storage that you need to keep by using the auto masking features. For large deformations, we have multiple reference stages that are being enabled. I'm going to talk to you about the current state of the facet matching and how this can also add capabilities. We have 3 bigger topics: nominal surface components, which we'll kind of go a little bit more in depth with an example with Jerem here, that's here with me. We're going to talk a little bit about the new controller that we're releasing in November. So all new systems will come with this new controller moving forward. But mostly we've also worked on the setup mode. So you'll also get that with the current controllers if you recently got a system, just to help us have template functionalities in when doing material testing and characterizations using a testing controller. And finally, the adapt exterior orientation is going to change quite a bit long-term usage of the system. We're talking earlier with you guys about the use of a system for long-term operations and being able to adjust the calibration without having to go through the entire recalibration is going to be a huge game changer using not just calibration objects, but any adapters that you would like to use. All right, so let's dig in. Again, if you have questions, and both for you guys in person, if you want to interrupt me, please do so. We have about an hour, so another maybe 50 minutes or so. I'll try to keep at least at 10 to 15 minutes duration for questions towards the end of this webinar. People that are joining us online, you can drop down questions in the Q&A. Ben, who's here with us as well, is going to filter them down. And we also have Jerem sitting with me here in our Seattle office as we're here for our Trillion Academy workshop in Seattle. All right, digging into GPU facet matching. This one's exciting. It is just going to help us measure DIC data a lot faster than before. We were just talking with you guys about facet matching and how the software is just doing whole calculations, breaking down the pictures into a matrix of numbers, and trying to sample the facets in left and right images and over time. Now, we've been able to parallelize most of this processing, and it's moving onto the GPU. Before, you'd have to kind of think a little bit more maybe about the optimal parameters, and the basic calculations depended on setting up, so it's an equation system, right, of how do we calculate the facets. And in the surface component creation, we had a couple of different computation modes that would sort of optimize the parameters together to give you a similar experience depending on the systems you are using. You had the options of using standard mode, high accuracy mode, or more points. These would toggle different types of equation systems, either bilinear equations, which along the length and the width of a facet, we would try to characterize. In this case here on this image, you can see from kind of brighter to darker. We would create a function line. I like to imagine it as a key, and we just build in notches in a key on both the length and the width. And then we go in the next image and we try to see, does this key lock anywhere on the next picture? So this function, this curve of ups and downs of black and white would be our equations to find in the next pictures. When we used bicubic, we were also defining a key in that diagonal of those facets. So and that's still going to be the case. We can do bilinear and have two keys or a third key in that dimension as well. The more dimensions we had, though, and the more points and the size of our facet becomes, the bigger and the more complex our equation becomes. Currently in standard modes, we usually had max sampling points turned on, and in high accuracy, we were running in bicubic, so as many directions of calculations as possible with an unlimited number of sampling points, which means that if you're using a 19 by 19 pixel size, you are using 1 point to discretize every pixels, and you would have a maximum of 361 points in the equation to define the functions. When in high accuracy, you wouldn't have any max sampling points. So if you were using 100 pixel by 100 pixels of a facet size, you could use the entire surface. Now, obviously, this could have a huge impact on computation speeds, and even doing more than 19 pixels and in standard, you would end up having fairly slow computation based on the number of directions that you're putting down. So by moving all of this this processing onto the GPU, we're actually able to move away from the CPU calculations and speed up the clock drastically. And so for equivalent sensors with the same project file, you can see here on a laptop at a Precision 770, regular 64 gigs of RAM, on a 12 megapixel project with 50 stage and 21,000 nodes on the surface. Fairly straightforward in some of those standard projects. We're looking here at already done in 2023 and a little bit longer in 2022. I mean, all in all, we're still looking at fast data processing compared to finite element analysis, and for the amount of data that we're collecting, DAC on an existing 2022 system is still really good, but to see these kinds of improvements, I think is just fantastic, honestly, across the board, and it will really drastically change the speed of computation for all of you. So we're seeing computation improvements here. I guess not the chart. We're seeing computation improvements here almost all the way up to fourfold, moving up to newer graphics card. But you can automatically activate this. There's nothing to check. There's no special parameters to have. If you have a compatible graphics card, you got one of our systems in the past 4 years with one of our computers, you have an NVIDIA card in it, and it will automatically use a graphics card to process your data if you open it in 2023. Again, so with the 5820, which is the standard kind of rack mount that we've had for about 4 years now, most of you have that system. We're using about twice the speeds. So you can see here 20 to 13. It's pretty common on most of our analysis. Now, some of you might also use it for live deformation tracking. If you're doing data, not just saving onto the RAM and then analyzing the data, but taking the picture in, taking the data and ditching them, the live tracking, if you're familiar with that, we're actually seeing increases almost another twofold, so 4 to 5 times faster when doing live tracking. So we're not saving the images. Long-term testings and point tracking, quite common with photogrammetry projects, super, super fast. So really excited about that. And again, as long as you have one of our systems from recent years, 2023, and boom, it's going to be faster. Okay, another little change, which is minor, but is finally bringing us a lot more contrast. We're getting a new surface color default. So whenever you're creating a new component now, it won't be gray anymore, actual green elements, and it matches with our concepts of nominal and actual elements. In the Explorer on the left-hand side, usually all of your actual elements are green. It's going to give us a little bit more contrast so you can do the selection a little bit better. Just realized that my face isn't really in there. Okay, the next one up is the change in a default measuring sequence, which currently would look like this. If you create a new measuring sequence from scratch and you don't save it to a template, you just have a fixed frame rate and image count range, which works fine. But we've actually just added that the default one always has a user input, so it can prepare your RAM, and then it will always show you the start user input. You can turn it off, but we realized that probably 90% of people were doing this rather than the other way around. And so maybe there's 10% of you that are going to be like, I don't need the user input, but actually most people are using it. So we're just flipping it to what's the most common use case. This will also have a benefit for anybody that's not using a full Correlate Professional line license. So we're adding features to our entry-level function here, giving you the option to actually synchronize a little bit better, especially if you're doing material characterization without the testing controller. You will always have the start input, so you can kind of trigger at the same time both your cameras and your load frame. So really cool. I mean, simple features, honestly, but we're trying to think about how to improve the workflows for everyone as much as we can. Another interesting one is the ability to create homologous projection points. This one might be a little bit tricky into when would I use this, but we've seen time and times again people saying, hey, well, I want to go from maybe the end of my project or from the CAD data, and here's my part, and I want to know what are the strain values at coordinates 100, 100, and 250. You can create the point right now in 2022, but it's going to be a nominal point, and it will only look for the closest node of this point in every stage. We now have the ability to say you can enter coordinates in any values, and it will find the closest node on the surface component and then track it over time, that specific node. So currently you have a point in space, and we'll just look for the closest node in 3D space. And if you go to the next stage, it will just still look for the closest node. But maybe initially it was node 200, and then that node keeps going down and moving further away. Now you can say, hey, well, in this stage, my closest node is 200. Now I want to follow 200 in the next stage in my timeline. Okay? So it's actually also quite good for scripting capabilities. We have a lot of people saying, hey, well, I want to always measure the same location, same points. Just find me the closest nodes, even though my surface is recalculated from something different. Build that up. I've seen this in high-speed data fairly often, saying, hey, well, I want to find the center point of a structure, and then from there, I want to find specific locations we were talking earlier about the ability to do 2-point extensometers on a tensile test. You can pick the center point, and then I say, okay, I want to have points at 5 millimeters, 10, 20 millimeters away from one another. And again, we can build those, and then from those fixed coordinates of defined measurements, project them on the surface, and then track them over time. So this homologous projection point is going to help a lot of different applications, especially through template options. Okay, it is achievable not as an inspection point, but as a measurement principle. We'll talk a little bit about that in the nominal surface component, but it's the idea of saying we can create something that is nominal. So in the virtual environment, in the CAD, in the perfect position, again, we say, I want to know the position 200, 200, 200. I don't know exactly where that point is going to be on my real part. That's my desired CAD coordinate. I'll find the closest nodes to it. So that point in CAD is nominal. It doesn't really exist yet. We're saying, how do I want to measure it? So applying a measuring principle of projection point is going to be how we're going to use this function. If you have more questions about all of those, we can obviously talk a little bit more about them. Specifically, I'm going kind of through rapid fire through them, but pretty exciting features. Okay, so again, we can create a nominal point to find the coordinates. Then you can switch to whatever stage you want to use as the connection point between the two positions. You apply a measuring principle of project onto actual, and otherwise you can construct the point and then choose the nominal point to project it onto. So both of them, but you're using the homologous progression if you want to track it afterwards over time. Okay, the next feature up is orienting measurement series. Some of you are using multiple sensors, and those who aren't, you can actually use your same sample to your same system to measure different angles of an object. We see this a lot in component testing where you want to maybe do step loading and say, I want to see this object go down to 10% load. I'm going to take pictures from the front, pictures from the back, picture from the side, and I want to stitch all of those together. That's my 10% load. I can create a stage for 10% load and bring in the pictures from multiple measurement series. We're seeing this also in kind of reliability testing where you can maybe impact an object or using 100 times, then bring it back, do another scan, see what the evolution is, and so on. This orientation measurement series right now is kind of hidden inside of the deformation series themselves. We're just adding more of a clear workflow, adding those into operations of measurements. So it's not going to be a sub-panel inside of editing measurement series anymore. This also makes it a little bit easier to script and to automate the orientation. And you can also see we have a couple of other ones here that we're moving away from inside of the creation parameters just to streamline the workflows for loading and exporting calibrations, but also the adapt exterior orientation feature that we'll talk about towards the end of the talk, and also 2D scale and calibration. Currently, if you want to do scaling and calibration with 2D, it's really kind of hidden again in the edit creation parameters. And now it's this kind of clear panel. So if you're doing, and we saw a lot of people doing it, especially with high speed, if you want to just use a single camera for something that's flat in space, doesn't have any out-of-plane motion, you could easily do 2D calibration using one of your calibration panels. And now the sequence is a little bit more clear and obvious as to how you would process it under measurement operations. Okay, so considerably faster orientations by doing it this way. When you build it up, you don't have to go and edit every individual measuring series. You can apply it to all of the measuring series at once. So you can see here the unoriented data and then oriented data seeing on that same component, just the data being mapped from both sides. So kind of neat features. We have some systems actually coming up for you guys pretty soon that will have up to 8 heads looking at the same part at the same time. So this will drastically improve your workflows and computation times of alignments. Okay, one of my favorite features this year, auto masking project images. We're getting more resolution year after year, more data, more speed. Great. We collect more data, but then we also have to store it and save it somewhere. And I'm sure you're all battling with full hard drives all the time. At least we are doing service works with you guys. This new feature allows you to really quickly and simply reduce your project by blackening out any pixel that isn't used by your analysis. It still gives you the ability to redo analysis and rechange your parameters maybe, but it's saying if I have data here, so this example here is a little excavator, which you may or may not have seen before that project. It's a little toy that just moves around in 3D space, and we're doing point tracking of the structure. It just looks at where are all those points on the image over the entire stage series, and if a pixel is being used by computation, we do an offset of a couple of pixels. In this case here, we have a safety margin of 20 pixels. If there's data in this, in any of the stages, keep that pixel alive, and then the rest of them, blacken it out. We currently have about 8 bits of data in each pixels typically, so we now reduce those 7 bits. We get rid of them and just shove 1 bits to 0, and the rest of them become dark, reducing the project file. Depending on the amount of empty pixels we're collecting, and it's always going to be the case, our surface is always going to be a little bit bigger than what we really need. We might have empty space between our grips if we're doing material testing and the actual samples. We might have bigger grips or bigger structures, but then a lot of empty pixels next to the thin dog bone. So we can eliminate that and drastically reduce projects. I think that's a really, really fantastic function. Any questions so far? I'm going super fast, but good. All right. Again, for those of you that are on the meeting online, if you have questions, feel free to drop them in Q&A, and we can circle back onto any of these features and show you a more live demo inside of the software afterwards. All right, my next one is facet matching with multiple reference stages. I talked a little bit about it earlier, but the idea that we can have, a tensile test, for example, that goes really, really elongated. And as it keeps getting elongated, those dots that initially were circles might become slowly thin lines, thin, long, flat lines. And so our facet, which started as a square, is slowly getting a thin, small rectangle. It's getting smaller and smaller away. Now, depending on the size we had, if this keeps getting smaller, we don't have enough width anymore to actually have a function we can fit along this width. If our initial pixel was 19, but then it gets stretched so much and now we only have 5 pixels, we might not be able to get a fit anymore. What we can do here is say, okay, well, after, let's say, 10 stages, I'm going to use the current 3D coordinate position, and I'm going to recalculate a new facet that's a square again. So it starts as a square, gets shrinking slowly, elongated, and then I'm going to redefine a new square after 10 stages that keeps getting elongated, and then it sets further stage, boop, another square, and keeps getting elongated. We used to have, we currently have in 2022 and onward and before, a function to do every stage of recalculation. The issue with that is that if you lose the point over time, it won't calculate for the rest of the project. If one stage doesn't recalculate, you're done with it. This allows us to go back to matching reference stages in the background. So for really eye deformations, we can have series of stages where we reapply a new facets instead of being just one facets over time. So really cool little feature using stage ranges. You can set up multiple matching reference stages. So adding up a new capability to surface component creations. This one is currently only available through scripting, but we can bundle it into a new surface component and have it pop up a dialog on its own. We can put these two together into one button if you need to. So basic scripting, but it's currently built up as separate stages. So we first start by creating a stage range by selection or by expression, and then we use that as, an input for the matching reference stages as an input into the surface component creation parameters. Okay. All right. We're down to our big 3 topics. So the ARAMIS controller, the nominal point, the nominal surface component creation, and finally the adapt exterior orientation. Starting with the ARAMIS controller here, just talk a little bit about it, but a couple of new features. So it's a slightly different format than the current controller. So it's a little bit thicker, but it has a lot more embedded built-in tools in it. It will come back at a slightly cheaper price where we're currently at. So that's the good news. We're not increasing the price. We're actually adding features and reducing costs. Talk about inflation being negative. We can now, as the first thing, is we can now connect more than one sensor to the same controller. We've added more power supply capabilities into one box. So you can use one controller to do those multi-head systems and do multi-component testing instead of needing 2 boxes on top of one another. So if you're doing multi-system measurements, this will drastically reduce costs. We've added more capabilities for PPT syncing. That's something you might not be doing much, but you guys might be doing a lot of. To synchronize with other tools and instruments, especially in aerospace and in government applications. You'll be looking at synchronization with other instruments. Using internal clocks with new Ethernet clock syncing is drastically going to help us, help you guys build good synchronization with your other tools. We have a 4-port switch in there right now, so quickly and easily do PTP syncing. We've added, like I said, more power supplies. So we have 224 volts now. We can power all of the lights, reducing from the current setup where we have a lot of external power supplies depending on your product lines and which cameras you have. Now they're all built into the controller instead of having multiple ones. We still have 8 analog inputs and 2 analog outputs built in. So we've added more BNC connectors directly on board and other types of port connections and BB9s as well. We have a USB connector that will, down the road, we have a couple of really good ideas to keep improving on the capabilities, but we're looking at improving Python and serial integrations, which will allow you to do also digital syncing and communications and synchronizations with other tools down the line. I think there's hopefully a soon future where we're going to be able to bypass analog outputs that is kind of more of a outdated, I want to say, platform as we move forward. We've been supporting Skippy as CPI feeds for a long time to stream data out, and we've connected with different vendors, be it HBM or National Instruments, but this is going to give us a lot more opportunities to bring in any other kind of tools, maybe Raspberry Pis and things like that down the line. So quite exciting. It's not quite there yet, but hey, we're laying down the blocks to just keep on innovating, which is really good. And finally, a really small thing, but it's a lot faster to boot than the current interface, which is just kind of really nice to not have to wait so long for the attention controller power button. Actually, before I mention that, but the other thing that is quite neat with it is it's also a lot faster because it's not so much of a server anymore. And we've gone away from depending on an external browser interface. Currently, if you had ever issues with it, you're kind of familiar with it. But talking to the controller requires us to go over Ethernet and go into a browser mode and set up Ethernet settings. And you can turn on and off the lights and things like that from that interface. You can also set up filters and so on from there. We've gone from this to building up the interface directly inside of the software as well, allowing you to build templates to automate analog signal inputs and outputs. Currently, you're probably all well aware, you have a load cell that has a load value as a 0 to 10 volt signals. You need to set up a conversion factor, and then you read it into the system with the ARAMIS controller and transfer that back into an a forced signal. We've added into the setup workspace new controller setup modes, which allows you to set up your and configure and define the analog inputs and outputs, as well as your triggers and filters. So there's no more web interface required, and you can save all of your settings and templates. So for example, if you're using always your machine for a 10 kilonewtons cell, you can create a controller template for 10 kilonewtons to read analog signal 0 is force and whatever factor. Maybe analog 1 is your crosshead, and so on and so forth. So building up those templates means you don't have to edit them or save it inside of individual project templates, but in your controller templates. Question on that? Okay, so setting up the analog channel is already a good improvement, but we've also added up a couple of filtering options to apply, improve the signal to noise depending on the machines what you're using, and applying filters also to triggering as well. So we have this setup channel mode that shows us live the current inputs of each analog channel that is being read, and we can apply live different moving average, for example, here onto specific channels and define the width of it. And you can see here on that graph, you can see the moving average is a black line. Obviously, by applying the moving average, we're adding delays, we're adding an offset, but that offset can then be compensated in the trigger setup as well afterwards. In the trigger setup, so the next workspace down, we have the ability to set up glitchers. So if you have signals that might be not super strong, or you have cable problems, bad signals for a push button, for example, this allows you to dynamically check your deglitching of the system. You can test out triggers with moving average, with various width, and you can see all of those as a preview. to see the live position of where is your current trigger right now on your analog signal. Now, adding on to this actually goes into fatigue testing. But if you want to therefore read in data and use, for example, the peak load at every signal to take a picture over 100, 1,000 million cycles, doesn't matter, we can read in the signal, apply a filter on the analog channels to smooth it out to have a really nice max peak channel. And then from the live preview that we can get reading the data in, we can look at setting up the trigger and the exposure time, which you can see here are shown live on your view. And you can offset it by 1 cycle. So even though you're applying filtering and slowly shifting your sample, we can then say, okay, well, from that curve, I'm going to take the next load peak, offset it off by half of that filter offset.
Is there a way to speed up the trigger? Sometimes we have like a up to 10-second delay on the camera system when we trigger the Gleeble. Or would that be in the Gleeble scripting to trigger heating later? Because we do rapid heating. So as soon as you trigger it, it's going to heat. And sometimes is there any way to mess with the...
Yeah, so depending on how it's set up, but yeah, there's probably various trigger setup that you could pick
Charles,
up.
Can you please repeat the question for the crowd?
Yeah, the question here was regarding the use of a Gleeble machine. And so if using thermal kind of preload, you want to see when you start the test based on that thermal response. Depending if you haven't, I don't know if you have an analog output on the Gleeble for thermal.
It's connected. So when we hit go on the Gleeble, it triggers the DIC. It's one unit.
Right. So the it's saying that the Gleeble machine does trigger the ARAMIS system. I forget exactly the setup, but I think you have an analog signal that starts the system. We could build different blocks. So we saw earlier the new default value is that has a wait signal. So the trigger pause is built in first before it just starts recording. And that's those new measuring sequence. Let me go back to that. So I'm on 26. Right, so this new measuring sequence that has the wait for signal of user input, we can actually use any of the trigger inputs or the analog signals, and we can use them with the filters that are applied. We could build that to either set an offset before, after, or say, hey, start recording a buffer of, let's say, 5 seconds, and as you're doing this, and when this finally starts, that's when you start recording and things like that. So there's different things we can do in the measurement sequence now using those filtered signals. For fatigue testing, I think this is really a massive improvements as we can really define exactly what's our exposure time, position on the curve of our load, and what's going to be our trigger signals, and when do we record the analog channels, and when does that start. So we can see this live all on the graph to adapt our trigger signals. Okay. Good. The next ones are the last big two. So 35, we've got about maybe 15 minutes to go. So the first one, nominal surface components, I'll let you maybe present it and then show the software. You can, I guess, click and then maybe share your screen to show your software. But you can click on this first to go to the slides. I'll let Jerem talk a little bit about that.
Cool. Yeah, thanks, Charles. So I'm actually really excited about these. It's some cool functionalities that we haven't really seen before that at least have been kind of requested from some users, and they've been kind of tough to do in the past. So this is going to give us a lot more functionality that I'm pretty excited for. But the main thing is, why have nominal surface components? Basically, it's for us to utilize some more complex measurements. So one is easily measure things again and again. We can template this and put it into kind of further testing as you do it over and over again. A lot of ways that we can create virtual strain gauges to exact sizes. So no longer are you kind of just estimating size or trying to get it by hand. We can put in exact values and have that correlate to an actual surface component. We can adapt it to work better with FEA. So if you bring in an FEA model with its own tessellation, we can use a tessellation of the FEA as the point distance in the software, which is really cool. We can also change reference lengths just by putting in values, which is also really unique and powerful. So yeah, talk a little bit about that, kind of looking at what I was mentioning here. The first image on the top left, right here, we're looking at just a basic surface component, just flat tensile specimen. But in this one, we're going to show you how to set a width and height and create basically a virtual basic extensometer size of your own choosing. No longer is it just kind of point and click where you want. On the right side here, we have also an example showing individual locations. Let's say your FEA or whoever's designing this test wants you to know the strain at an exact location. We can then input that point nominally based off a CAD model or an FEA model and get the strains basically projected from that point throughout the test. Bottom left here, we can also use CAD patches or just CAD points in general to create a surface component. And those will kind of make more sense when we go through all the analysis together. And then lastly, bottom right, we can also, if you have a really complex shape here, we can choose different patches of that CAD, create the surface component based off of that. And then once everything's aligned, we can have a surface component built basically automatically on that location, which is really accurate, it's really cool, and a really powerful new feature, I think, for our analysis. Sorry. So multiple different ways that we can create these nominal surface components, from simple planes, like I mentioned, selected areas of CAD or CAD patches, FEA data, planar sections, meshes, and we can even create user-defined XML files kind of through scripting options that we can use to create these surfaces as well. So a lot more flexibility in these creations. Something I'll note here, the facets are created for these in millimeters. So no longer are you going to put 19 by 16 pixels for like your facet and point distance. It's going to give you a physical value we're going to want to input there. So just keep in mind that's kind of basically why we're using these nominal elements to give you that defined size that you want. And create actual surface components still generate really good results. You don't necessarily have to use these nominal surface components. It's just an additional feature that can help you in the future for more complex tests. Some very important kind of requirements when using these, we must be able to identify what they say stochastic pattern, but basically a speckle pattern on the surface. If you don't have a pattern, obviously we're not going to be able to pick up any surface component. And having a proper alignment is also very key for these. The term nominal just basically means that we're using either a CAD model or an FEA model, and having a good alignment with your actual data and the CAD is very important for these to actually make sense in your data. Otherwise, it's just kind of not even a good comparison. So simple planes. So first off, we'll look at this. We'll look at all of these basically as some analysis here. I'll kind of just skip through these a little bit quicker, but we're going to go through all of these projects here. But first off, showing you a simple plane we can create a surface component from that. Just some requirements. It does need to be a flat surface, obviously, to match with a flat plane. Another component or another analysis method we can use here is we can create points on our CAD model and create small, basically strain gauge rosette regions. So we can say, hey, I want to define a region 10 by 10 millimeters on the surface and get the strain average in that location as basically a strain gauge rosette that you would, in reality, glue down physically on your surface. Obviously, nearly flat is optimum for these, but it would be just the same as if you're trying to apply a strain gauge on a curved surface. It's going to give you the same data results. It's going to project onto that surface. Again, good alignments are always key with any of these nominal surface components. And just highlighting again, all of this can be templatized, basically put into project templates for being used over and over again for different tests, which is pretty cool. CAD patches, like I mentioned, we can select different zones and regions or patches and create surfaces just based off of that in the CAD. Pretty cool. Again, restrictions, we just need to make sure, obviously the tessellation of the CAD or FEA is what's going to be the point distance for those surface components. And there are some interesting things with edge errors if that is something you're looking at. So just keep in mind those restrictions. Okay, I think let's just, an XML file here. We can export, and you could previously do this as well. You can export your actual surface components as an XML file, and if you open it up here, it will give you the location of the kind of triangular and center point regions across the entire surface. And so you can go in here and optimize exactly how large you want each of these to be. You can have kind of non-standard shapes for your facets. And different things like that. So you can really customize this to your needs if you desire. And this is our planar section. We'll kind of show you this as well. But in order to create sections based off this kind of complex geometry here, we're actually going to use what's called a silhouette section. That's something that's, and with all of this nominal components, this is kind of something we don't normally teach in some of our kind of initial courses. So this is all going to be a little bit more new. We're going to talk about a few different things in these, but just keep that in mind. And again, proper alignment is key here. I'll just show this briefly here. You guys can rewatch the video if you want to, but kind of this gives you some when to use certain types of nominal surface components for different use cases, basically. But I really want to go on to show you some projects here. So
Go ahead and show the simple planes really is the one that we...
Okay. All right, so here we have a typical tensile test project. Sure. Make sure. Is it sure?
No.
Yes. Perfect. Okay. So here we have a typical tensile test. You can see here I have a reference image at the beginning. If I scroll through my timeline, you can see pulling down our sample, and eventually we have failure here. What we've done in this project, we've placed a center point fairly close to where our failure point is here, and we want to create an extensometer of 50 millimeters in length based off that center point location. Previously, this was pretty difficult to do with just creating actual surface components. You'd have to create some points and distances and try and match those up together. But now it's actually quite easy. So first off, we do have an actual surface component created here. If we look at our Explorer tree, we do have an actual surface component created so that we can get this center point. But from here on, we're going to start to create some nominal elements, basically CAD elements or elements that never change. One thing we'll need to know before we start anything here, we've created a good alignment. So we have a 3-2-1 alignment here, such that our Z-axis is planar with our surface here.
That can be done in testing with different tools. So we did a surface which is kind of inherent to what we want, but we could use uncoded targets that would be repetitive to say, hey, I always have those targets on my grip. I always want to create a surface that's in between the grips, halfway in, project that location, and this is where we want to have our surface. So you could use other tools to do the alignment. I would probably use uncoded markers on grips or on my fixtures.
So what we're going to do, we're going to create a center nominal point. So we have the actual component here. We can just copy, Control-C, Control-V. We can create a center point copy here. I'm going to rename this really quickly to call this a nominal center. So this is our nominal center point on our region there. We can actually go to Operations, Elements, and we can convert that to a nominal element. You notice here you get this error here. This is something, if you haven't worked with nominal elements a lot, you will see this often. This basically means we need to apply what's called a measuring principle to this nominal element, basically telling it what we're comparing it to in the project. For most of this, we're going to use what's called no measuring principle. We're not going to utilize any measuring for that. What I'm going to do is just right-click on it, go to the very top here to measuring principle, and say no measuring principle. And that error goes away. Next, I need to create a plane based off that nominal center point. So if I go to construct here, you go to plane, and I'm going to create point normal plane. Here I can select that nominal center I created. And then the normal direction, since we have a good alignment here, the positive Z direction is our planar direction here. So this is going to be our nominal plane 1, say create and close. Again, we need to give it a measuring principle. You'll see that error there at the bottom. So we need to left-click on our nominal plane, go to measuring principle, and no measuring principle. Next, we can create the size we want for that. So I was saying basically we want a 50 millimeter long extensometer region. So what I'm going to do is double click on my nominal plane 1, open up my properties tab here. I'm going to go to size. And instead of using the calculated size, I'm going to say, okay, I want my, and it's a little bit inverted here. The length is in the Y, or excuse me, the length is in the X direction, width is in the Y. So I'm going to put in the width of my specimen. So it's about 12.5 millimeters across here. And kind of important that we have it going to the edge of our surface speckle pattern. Next, my width is going to be that 50 millimeters extensometer size I want. So there's my nice region I've created. That's all you need to do there. You can hide your properties tab now. And now we can see our nominal plane here.
Just a quick pause here. Obviously, this setup is a template setup. So once you have this done, you could create it from a project that doesn't have any data. So the engineer that's requesting data can say, hey, here's my template. I want a plane that is in this size from 0, 0, 0. I want that data strain information. They would get you, therefore, the nominal plane just built in. It doesn't have to have any data. And then we build a surface off of it. We kind of did it the other way around, saying, okay, we have data, let's build a template from it, building a plane, and now we can reapply this over and over. But once you have a nominal point in the center and the nominal plane, you could reuse this on 100 different projects and just automate them all one after the other. And that's really where the power of these become handy is. You can have lots of different locations or for width of surface and just automate their creations and their calculations on the next project. So.
And all these features so far we've talked about, these have been in existence through pretty much all the software functionalities from the past. We're going to get to our first new functionality here. So if you go to Construct and then go down to Component, typically you'd see your surface, your facet point, your points. Now we have Nominal Surface Component option here. So if you click on this, let's expand this out a little bit so you can see everything. Here we can give it a name, obviously like our typical in the past we do. We can give it the sample, tensile specimen. This is now going to be based off of that nominal plane that we created. So you can see here it's starting to give us some preview facets on the surface. And you see our facet size and point distance are now solely in distances, millimeters, inches, mils, nanometers, whichever you'd like here. You do have the option, so in this version it doesn't show it, but when you hover over it, it will basically tell you that 0.84, whatever, correlates to 19 pixels, basically. This button next to it with the little refresh icon here basically brings it back to the 19 and 16 for the default sizes. So if you want a 19 by 19 pixel and 16 point distance, you would click those buttons and it would compute that automatically for you. Here I'm just going to leave that as is, but if we had, if we wanted to mess with our facet size based off our speckle pattern, we could do that as well. We could change it to make it have those 3 to 5 speckles that we need here. From here, I'm just going to say that's everything's good here. There is this checkbox here for extend points onto boundary. So you can see at the edge here, it is creating these facets all the way to the edge of my speckle pattern. If I uncheck that, it would do that. It would basically restrict it to the inner portion there. Especially since this component reaches the edge of my part, I'm going to make sure that extends to the boundary there. I can say create and close. Now again, with the same thing as before, if we go to our nominal elements here, our components, I need to give this a measuring principle. So again, you can right-click on it. You see here I open up the I inspect wheel, and the T icon here also gets you the measuring principles. And in here, I'm going to use the identify surface component. So now it's going to look for that speckled stochastic pattern behind that nominal component. If it finds it, great. It'll show you some green actual facets here on the surface. Here, basically as before, when you create an actual surface component, you'll have your computation types. So you can, again, use standard, get more points, high accuracy. You can also change your facet matching, your tactic component, and other options still here. This is also a time when you can check, for instance, intersection deviation, pattern quality, your different quality checks. If you're happy with this, you can say OK. Now it's going to recalculate here. Again, utilizing the new GPU calculation for facets, so it's pretty quick. For 90 stages, we can see how many data points, 1,500 data points, pretty good. But now we have our typical kind of surface component here that you'd see by creating an actual surface component. But this is a 50 millimeter distance now. And at that point, we can create, let's look at displacement, excuse me, epsilon y. Let's look at the average in that region. And this will basically give you comparable results strain-wise to kind of a 50 millimeter extensometer from typical calculations. So a pretty quick workflow, but hopefully not too crazy or anything, but it just highlights kind of how in the past I would take a lot more steps and a little bit more finessing to try and get something that.
And we use things that were existing on the sample, but again, we could have just constructed a point and say L1 0, 0, 0, enter, create a surface of 50 by 50 around this zone, and it will build it up for you. It makes not as much sense, I guess, in metrology testing. It's a little bit, it could be helpful for project templates, but if you have a complex structure, that's really where it comes in super handy, just like the homologous points, where you can say, hey, my FEA data points are this, 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 and that. I want strain values of 10 millimeters by 10 millimeters on all of these locations. So for component testing, it's a massive, massive improvement.
Cool. Now there's some other examples here. Since we're kind of low on time, we can, if you'd like us to go through these with you, feel free to contact us and we can set up a little meeting to kind of run through creating the rosettes and these other points. But let's go ahead and talk about really quickly the adapt exterior orientation. So this is a new feature to better help kind of support challenging measurements and setups. Also give you some tools for smarter preparations and how to kind of rescue your data. Now we say rescue data, we're kind of referring from a basically a bad calibration that occurs, or let's say something happens and our cameras are decalibrated during the test. We can go back and kind of save that data that previously that we couldn't do in the past. So our general procedure in the past was setting up and calibrating the sensor, create your reference stage, check your intersection deviation to check if the sensors were still calibrated. You do your tests and then analyze your data. But there could be some other considerations occurring for your tests that could increase your intersection deviation. So things like thermal currents, thermal impacts, basically, vibrations, and kind of general mechanical impact. Even like moving the sensor, potentially somebody could bump into it and decalibrates over time. Obviously, we want to avoid these kind of occurrences from happening, but in some applications it's not possible, right? So explosion testings are going to have a shock wave, crash tests, and you can even mount the sensor inside sometimes of the vehicle, and it may just vibrate and things like that. Lots of other applications here, basically, that occurs with. So with a typical calibration, what we're doing is kind of constructing or basically telling the software how to reconstruct the 3D data from the two images. And that consists of two parts. We call them an interior orientation and an exterior orientation. So on the right side here is a little diagram. We're kind of showing our two images, looking at our object here in the 3D field. Basically, our calibration depends on a lot of different things: lens distortion, we call it chromatic aberrations, focus, aperture, and like the position of the lenses on the cameras themselves. So the interior orientation, all of this here, is basically based off the lenses and how they're mounted to the cameras. And then we have what's called the exterior orientation, which is basically how the cameras are oriented to each other. So the left to the right camera, the distances and rotations and angles and things. Now this is what we're going to focus on for this adapt exterior orientation. Is basically when we're moving our cameras or something could bump and tilt one of the cameras. That's an exterior change, and we can fix that. We will note that we cannot change the interior orientation. So if you were to loosen the threads on the lens or change the aperture, you would have to do a full new recalibration to fix that kind of change. This is more of just like for shock waves, loosening over time, kind of tilting, things like that, rotations.
One point that it's not a full recalibration. It's not even a small recalibration. It's only adapting the exterior orientation, which means you can still have a lot of errors. If the cameras got closer, further away, or up and down, it might create parallax effect and other issues in your measurements that isn't going to be taken into account here. So your data could increase or get worse in quality and in noise levels, especially if you're looking at displacement values.
And significant change, obviously, when you look at intersection deviation, right, our typical max is like 0.3 pixels, so not very much at all in terms of how much is allowed, basically. And as that intersection deviation rises, you will notice that your projects will no longer kind of recalculate at a certain point, and you'll lose that data. So you can see here, this was like that's an abrupt change. Something happened on that top right plot there that shifted the intersection deviation throughout the rest of the project. And then the bottom right, we have an example of something that gradually shifted kind of over a few different stages. We can fix both of these different changes with this adapt orientation or exterior orientation option. So what's going to happen is basically for the first one where stages are basically changes in one stage, we're going to keep the old calibration for the first 10 stages here, but then we can adapt that calibration for 11 and on basically for the rest of the project. If there's like multiple stages here where we have a changing intersection deviation over time, we can select all of those stages, create a stage range with that, and we can use that selection now to basically adapt the orientation during that time frame. So this just shows a little bit what it looks like in the software here, our general procedure that we're going to have. But maybe we should just skip to the actual, yeah, we can just take a look at it in the software. Okay. Okay, so I'm going to go and open up a quick project here. So this is that first project where it's going to look at our, presenting, geez, let's do it every time. Okay, there we go. Okay, adaptation A. Okay, so let's take a look here at our folder, I think. So I'm just going to do a quick inspection here. Inspection, check dimensions. Okay. Jeez.
Does that show you?
Yeah, we're going to go. All right, so over here, I inspect my surface component, so looking at the average intersection deviation across the whole surface here. So you can see over time we have really good intersection, very, very small, 0.019 pixels, well within our limits. And then we have some abrupt change here that occurs. Now our intersection deviation is 0.8, so well above our 0.3, kind of the maximum we'd like to see. And it stays there over time. Now you can see the bottom right of our screen here, we're actually no longer able to calculate some of our data results, especially from that holder there at the bottom. And that's something that you can see as well in your projects that may give an indication of intersection deviation change. So what we're going to do is go into operations and measurement, and we can go to adapt exterior orientation. So in here, since we're just using the one stage to change, we're going to let's click on stage 11 here. Stage 11. So that's our first stage. That's when the intersection deviation gets too high. Then go to operations, adapt. Now, in order to utilize this tool, we do have to have something in our field of view that is rigid over time, that's not changing. So you can see in this project, for example, we have our adapter here, based on our holder for our object. The front plate here is steel. It is not moving internally over time. We do recommend that if you're going to use this tool, even spreading out some points around your object of interest can help with this whole exterior orientation. The more points you have and the more spread out, the better, basically. So we're going to utilize our holder point component here as that adaptation tool. So our point observations are going to be the surface component of interest. Our scale observation is going to be that holder. And you can see here now it gives you a preview of the adaptation of the exterior orientation. So basically now we can see our point component again at the bottom. It's actually calculating correctly. And then we do have some other options at the bottom right here if you need to. If we had a stage range, we would choose the stage range here as the computation ranges. And then we can just say, okay. Do a quick recalculation. And now you can see from our intersection deviation diagram here. Let me try to make it. Go. We can see that we still have the same values as before here, but once we had that giant shift up, we've now adapted the calibration to be much lower. And they're both well within the range of each other's values, basically here.
Can you Control Z and look at the sigma of strain before we change to go back one more? More before adapting. Yeah, there it is.
Sigma strain.
Yeah.
Okay, let's adapt.
Average maybe also?
Average, yeah. So here Charles was just asking if we can look at also the average strain in the y direction and the standard deviation strain in the y direction as well. So we're kind of taking a look at both of those over time here. And then as we reapply our adapt exterior orientation again, go, say okay, calculate. Change.
Well, you can see the strain levels is staying consistent, but that we're able to calculate displacements now because the points are back to a normal intersection deviation. The key aspect here is the thing that you can reset your external orientation as long as you have a point component in your field of view. You can also use a surface, but it's a little bit trickier to use. That means instead of having to put a calibration panel back in your field of view if you want to adjust the calibration, you can use any known object. You can use this fixture. Long-term testing that we see is you might have the cameras on a bar, and just because of temperature in the room, it might get shorter or bigger, and that will impact your calibration, your external orientation. You can adjust this and saying, well, the points there did not move on my rocket that I'm testing, and all I want to do is redefine where my cameras are based on these points and then do more measurements. We've used this in high-speed scenarios where we have the sensor aimed in one location, the test rig is 90 degrees away, and we need to move the cameras, but there's no room to do the calibration where the test article really is. So we have the system in one place, we calibrate it, but because of that system not being stable enough and with really long abnormal lens, it ended up decalibrating by the time we're moving back. So we took a picture of the artifact, of the object itself that we were measuring that had point components on it after calibration in this void space. Then we moved everything, put it into the area where we're actually going to be measuring, took another set of pictures of that object now in its actual position to reset calibration. And now we're ready to shoot our test data.
So I was going to what Charles is saying, basically, if we go back to our operations and adapt external orientation here. So for instance, what we could do is like we could calibrate on the ground, we could hoist our sensor up into position basically. And then we can also have something up there in the field of view that we've already kind of pre-scanned for its reference XML point cloud. And as long as you see those points in that first image, you can take a reference image of just those points. Then you would choose basically your surface component, you would choose those points here. Then you would select against nominal, or excuse me, against reference date, you'd select nominal, which is those reference XML points. And then you can say overwrite sensor calibration for further measurements. So basically, assuming that when you hoist it up, basically somebody, maybe the camera's tilted a little bit more or something. Now, from every test base you take from then on, it will overwrite your calibration with that new orientation. And then the rest of your tests, you can basically delete that first image with the reference points because the calibration is already saved. And then you can take your actual test points as you put them. And here I'm just kind of showing off, basically, again, a reference stage here. And I created a stage range for that area where the intersection deviation was bad. And then okay here. And now it's readapted. Now I can see those points still.
So this function is going to be really good, more for troubleshooting and for high-speed imaging, but it might also have an impact if you're doing long-term testing. your use cases. If you're not using a system for a while and you want to keep the same volume, you can readjust it based on, somebody might have touched it, or you come in the next morning and there's maybe a little bit of a decalibration. Without having to redo a full cal, you could just take a picture of your node calibration object to reset things down. Okay, we've gone a little bit past times, unfortunately, but hopefully these different functions are a good overview of some of the 2023 features that we have to offer now. And yeah, I mean, if you have an active software maintenance plan, you can already upgrade to it. The GPU facet matching is in and out of itself. Only that, a game changer and sufficient to justify moving up to 2023 as soon as possible. We'll send you email blasts whenever we're ready to send the license updates, but be on the lookout for that as well. It's going to be this month. Okay. Is there any questions on these features, or maybe thinking, how could I use this or not?
Cost is the upgrade.
What was that?
Or license. Cost is.
Walter would have to check based on what modules you have in there. There's typically a reentry fee, so if you haven't been on maintenance to upgrade it, and then you have a year, so you'd also get next year's software as well. But yeah, Walter would be able to calculate the price. It's usually about 10 to 30% of like a full new license. So it's a lot cheaper. It depends on the modules and whether or not you expired or not. The actual just maintaining is fairly cheap. If you have to pay the reentry, that's when it comes a little bit expensive, of course, and kind of doubles the price. Any other questions? I think pretty much everybody online is leaving us already, so I think we're good.